In this video, we're going to start solidifying some of those derivatives that we've seen, especially with polynomials. We know some derivatives of polynomials, okay, because of what we did with Pascal's triangle and the direct definition of the derivative. So in this way, we're going to use specific rules that can calculate derivatives, and we'll know that some differences, and that'll be sums and differences this time, we won't do products and quotients yet, that's coming up, can be differentiated using certain derivative rules. Okay, so one of the things that we've already seen is the derivative of a constant. The derivative of just a number like c. And we know that that happens to be 0. Because, which makes perfect sense, a constant, it's unchanging, it's the same all the time. And a derivative is the measure of a rate of change. Well, if something is constant, it's not changing. So it makes sense that its derivative would be 0. At the power rule. So our most basic power rule is this one. The derivative of x is 1. We also have the derivative of x to the n power. This is the power rule. And that is n times x to the n minus 1 power. So we bring the exponent out front, multiply it by any number that's there, and then drop the exponent by 1. And we've seen some of that as we did our stuff with Pascal's triangle and learned a little bit of the shortcuts there. Okay, multiplying a derivative times a constant. So the derivative of cf of x. So c is just a constant. What we can do with that is take the c out front and then take the derivative of the function and multiply c times the derivative of the function. Okay. The sum rule says that the derivative of a sum equals the sum of the derivatives. And this is, it's not a rule we think about much. We use it all the time, but we don't think about it. What it really does is allows us to take different terms of a larger function and take the derivatives separately. Anything separated by an addition sign, and soon we'll see by a subtraction sign, we can take those derivatives separately and just add the derivatives or subtract the derivatives. So the difference rule is very much the same as the last one. It's just the difference of the derivative of a difference equals the difference of the derivatives. And again, that's a rule we use all the time. We don't even realize that we're using it. Okay, one of our most basic derivatives, and I always tell kids it's the hardest. Okay, the derivative of y equals e to the x. And we might go through proof on this later, but the derivative of y equals e to the x. Y prime is e to the x. It's its own derivative, and it's the basis of a class of functions that are their own derivatives. Okay. Now if we have a general exponential function here, this is an exponential function. Okay. And the derivative of that of any general exponential function is y prime equals the natural log of the base, so the natural log of a times a to the x power. Now you might say, why does that work with e? Well, it certainly does. So if we have y equals e to the x, then y prime would equal the natural log of e times e to the x. However, the natural log of e is 1. So that, of course, would just drop out. It'd just be e to the x. One of the derivatives is going to expect you to have memorized y equals the square root of x. And we'll go over a proof of this, a short proof of it later on. It's 1 over 2 root x. Good. Alright, so let's look at some examples. And as I said, some of this you've already done. and so some of this will be pretty easy for us. First of all, the derivative of 200. F prime of 200, well, that would be 0 because we're taking the derivative of a constant. The derivative of a constant is always 0. And 200 is just a number, it's just a constant. So now we're going to take the derivative, g prime. We want to know what g prime of 3x. Well, we already know that that is just 3. When it's just x, it's x to the first power. 1 times 3 is 3. Drop the exponent, be x to the 0 power, which of course just drops out. But we've seen that before. Along with, we've seen this before as well, another example of the power rule. And we know to go 2 times 7 is 14x. Drop the exponent by 1, so it's just x to the first. Now the next one, not only are we going to use the power rule, we're going to use it 1, 2, 3 times. Okay. We are going to use the sum and difference rules because these are separated by addition and subtraction. So remember, all that really means, those sum and difference rules, is that we can take x to the fourth, take its derivative by itself, and then move on to the next piece of the function. The derivative of x to the fourth, it's 4x, and then drop the exponent by 1, 4x to the third. Minus 3 times 2 is 6, x, drop the exponent by 1, 6x squared. Now 5 times 2 is 10, x, drop the exponent by 1, it's x to the first. And then the derivative of minus 3 is just 0. It's a constant. Derivative is just 0. Those are ones that we've seen, that we've worked with. Let's continue on. So the derivative of y prime of 6x, that's an exponential function, and we had a rule for that back here. Our derivative, here's an exponential function right in here, just like this, and here's our derivative, the natural log of a times a to the x. So it'd be the natural log of 6 times 6 to the x power. Now we're going to do the same thing here, except we're going to multiply our derivative by 5. So y prime would equal 5 times, and then the natural log of 2 times 2 to the x power. Now in this case, for right now, we only have one way of doing this, and it actually would be the quickest way, really no matter what, but it would be to distribute this. That'd be 2 to the third, x to the third, which is 8x to the third. Okay? And the derivative of that is 3 times 8 is 24x squared. Okay? Later on we learn a chain rule, which we could also do that with the chain rule, but it's a pretty simple one. Alright, we already know this one. We said it's 1 over 2 root x. Alright, so next, y equals 4 square root of x. Well, we know the derivative. This is going to be, y prime is going to be 4 times the derivative of the square root of x. That's what a constant times the derivative tells us. Well, we already know that the derivative of the square root of x is 1 over 2 root x. And this 2 and this 4 are going to cancel, and then the 2 is going to multiply by 1. It should be 2 over root x would be the derivative of 4 over square root of x. Alright, now we have some special cases of the power rule. Things that you've been taught not to do, we are now going to tell you to do them. So for example, if I have f of x equals 1 over x cubed minus 4 over x to the fifth. Okay? We are going to do the unthinkable, at least in algebra land. We are going to write those with negative exponents. So we have a positive exponent on the bottom. To make it have a negative exponent, we need to move it to the top. So this would be x to the negative 3 minus, and then we have the 4, and the x to the fifth would come to the top and become x to the negative 5 power. these two are equivalent. You could convince yourself by graphing them both on your graphing calculator, you'd get the same graph. So what we have is this function f of x equals x to the negative 3 minus 4x to the negative 5. Now we use our power rule. So it would be negative 3 times 1, negative 3x, and be careful, negative 3, drop the exponent by 1, it would be negative 4. And then negative 4 times negative 5 is positive 20. X, and negative 5, drop the exponent by 1, it would be negative 6. Okay, so this is our derivative. They would not, now this is fine actually. There's nothing wrong with this, it's right. And I'd be happy if you stopped there, but on a multiple choice test, they're not going to do that. They're going to make those negative exponents back to being positive by moving them to the bottom. So negative 3 over x to the 4th plus 20 over x to the 6th, okay, would be our ultimate derivative. Both of them are derivative. This is in a more simplified version, or some people could consider it more simplified than that one. And that's how we have negative exponents. Negative exponents are basically treated the same as positive exponents. All right. Suppose we have this. This we can rewrite without a radical symbol there, and it would be x to the b over a power. The root always goes on the bottom, and the power always goes on the top. So let's use that. Let's do a proof that the derivative of the square root of x equals 1 over 2 root x. We've showed you that, we've told you that, but we haven't proven it yet. We're going to prove it right here. So y equals the square root of x. One of our rules is that we can take this is a square root, so there's a 2 there, and it's x to the first power, so it's x to the 1/2 power. X to the 1/2 power is the same as the square root of x. They mean exactly the same thing. Okay? But on this we can use our power rule. So the 1/2 would come out x, and then 1/2 minus 1 is negative 1/2. So it's 1/2 x to the negative 1/2 power, which we can do something with that. 1 over 2, and since this x to the negative 1/2, it goes in the bottom of the fraction now, where the 2 already is, and now it becomes positive, the positive 1/2 power. But we learned over here that x to the 1/2 and the square root of x, those two things are equivalent, so it becomes 1 over 2 times the square root of x. That's where that rule comes from. Okay? But I, of course, want you to memorize the derivative of the square root, so you don't have to calculate it each time. All right, let's do another one. Okay, so let's do f of x equals the 4th root of x cubed. We want to find f prime. Okay. First of all, rewrite it as x to the 3/4 power. Now, once we rewrite that as x to the 3/4 power, f prime would be 3/4 x, and then to subtract 1, there's an easy way to do that. Take the top 3 minus the bottom. 3 minus 4 is negative 1, and then keep the denominator, negative 1/4. So that would equal 3 over 4 x to the positive 1/4 power, and then convert it back to a radical. It would be the 4th root of x to the 1st power. So ultimately, all of these are the same thing, and I'm fine with this right here is fine as far as I'm concerned. But of course, on a multiple choice test, they're going to write it with the positive exponents and with the radicals in there, more than likely. Okay, so, but you could write it this way, and actually putting it in our calculator is usually easier in this first form here than it is certainly over here. This would be a pain. This is very easy. All right, good.